Welcome to the Deep Dive. You're here because you want to quickly understand what's important in healthcare data analytics, and, well, that's what we aim to do.
That's right. And today, we're looking at something pretty specific, how computer algorithms, clever ones, are being developed to predict health outcomes.
Yeah, and digging into a particular piece of research here, it's focused on making these predictions not just super accurate,
Which is crucial, absolutely paramount in healthcare.
but also really fast.
Yeah.
And that speed matters a lot, especially for, say, your phone or wearable devices, things that don't have massive computing power.
Exactly. Getting those insights when they're actually useful, without a big delay.
So the paper, it's titled Resource-Efficient Fast Prediction in Healthcare Data Analytics, a Pruned Random Forest Regression Approach. Quite a mouthful.
Ah, yes, but it gets straight to the point. They're tackling that core challenge, getting speed and accuracy.
And they didn't just theorize, they tested their approach. This specific technique they developed using real medical data, stuff on diabetes, breast cancer, and Parkinson's disease.
Right, that's important. Real-world data. The technique itself is called CLB-DRF.
CLB-DRF. Okay.
And our mission, really, in this deep dive is to unpack how this CLB-DRF method actually works.
What makes it tick?
Yeah, and what their results suggest for, well, maybe the future of how health predictions are made and used.
Okay, let's jump right in then. Why this focus? Why is balancing accuracy and speed such a big deal in healthcare analytics? For you, the listener, why should you care?
Well, accuracy, it's almost self-explanatory in health, isn't it? It's just vital.
Can't afford to be wrong often.
Exactly.
Yeah.
The paper really hammers this home, but low accuracy can lead to serious consequences. Think misdiagnosis, ineffective treatment.
Or worse, yeah. Okay, so accuracy is non-negotiable. What about the speed part? Why is that so critical?
Speed becomes really important in a few scenarios. Think about mobile health apps.
Like on your phone.
Right? Or wearables, maybe a fitness tracker or a smartwatch you use. These devices have limited power, limited memory. If the prediction algorithm is too slow, too demanding, well, it's just not practical for everyday use on those devices. You need the info quickly.
Yeah, if your watch takes 5 minutes to tell you something about your heart rate pattern from the last hour, the moment might have passed.
Precisely. And it's not just personal gadgets. Think about real-time monitoring in hospitals or even spotting disease outbreaks early. Fast analysis is key there too.
Makes sense.
And the whole field is booming. The paper mentions a prediction, though it's a bit dated now, from 2016, about healthcare analytics becoming like a $34 billion industry by 2022.
Wow. That shows the interest and the perceived value, definitely.
It does. It underscores why everyone's pushing for better methods, faster, more accurate ways to analyze all this health data to actually help people, improve outcomes, maybe even prevent issues.
Okay, so accurate and fast. Got it. Now, this paper leans heavily on something called random forest. Can you give us the simple version of what that is?
Sure. Think of random forest as a powerful tool for making predictions. It's what's called an ensemble method.
Ensemble. Meaning?
Meaning it combines the outputs of many simpler models, in this case, decision trees, to get a better overall result.
Ah, like asking a whole committee of experts instead of just one.
That's a great analogy, yes. It averages out the individual perspectives or predictions of many trees to arrive at something more robust and hopefully more accurate. It was developed by Leo Breiman, a well-known statistician.
Okay, a committee of decision trees. How does it make sure these experts aren't all thinking the same way? You need diversity, right?
Absolutely. Diversity is key. And traditional random forest has two main ways it builds that in. The first is called bagging.
Bagging. Like putting things in a bag?
Sort of. Imagine all your patient data is in a big bag. For each tree it's going to build, it doesn't use the whole data set. It takes a random sample from the bag with replacement.
With replacement. Meaning some data points might get picked more than once for a single tree.
Exactly. And some might be left out entirely for that specific tree. So each tree learns from a slightly different slice of the overall data. About 64% unique instances typically go into each tree's sample, leaving about 36% out of bag.
Okay, so different training experiences for each tree. That's one level of diversity. What's the second?
The second happens inside each tree as it's growing. When the tree needs to make a decision, like splitting the data based on a patient characteristic.
Like age or blood pressure.
Right. It doesn't look at all the possible characteristics or features to find the best split. It only considers a random subset of those features.
Oh, interesting. So even if blood pressure is the absolute best predictor at that point, the tree might not even look at it.
It might not, if it wasn't in the random subset selected for that specific decision point. This forces the trees to explore different predictive factors and makes them less likely to all rely on the same few strong predictors.
Got it. So, random data samples and random feature choices. That creates a diverse forest. And the paper notes these trees are usually unpruned, grown all the way out.
That's the standard approach, yes. Grow them deep and bushy. The idea is that combining lots of these complex, diverse trees averages out the noise and overfitting you might get from a single deep tree.
Okay, that sets the stage for the traditional method. Now let's get to the core innovation here, CLUB-DRF. What's the big idea behind this approach?
The main goal of CLUB-DRF is essentially to take that potentially huge random forest, what they call the parent RF,
The starting point.
right, the big one, and then intelligently prune it down to create a much smaller forest that is ideally just as accurate, maybe even more so.
But significantly faster.
Exactly. Faster and more resource efficient because it's smaller.
Okay, pruned makes sense, cutting back. But how do they decide which trees to keep and which to toss out? Is it just random?
No, not random. This is where their novel technique comes in. They use clustering.
Clustering, like grouping similar things together.
Precisely. But instead of clustering patients, they cluster the trees themselves based on their prediction patterns. It's a way to introduce, or maybe recognize, a third kind of diversity or perhaps similarity structure.
No. Clustering the trees, how does that work? What are they clustering?
So first step, they build that big parent RF. In their study, they used 500 trees.
Okay, a big forest.
Then they take the training data, the data used to build the forest, and they run it through each of those 500 trees.
So each tree makes a prediction for every patient in the training set.
Exactly. So now for each tree, you have a whole list of predictions it made. Think of it as that tree's prediction signature on the training data.
Right, a vector of predictions for each tree.
You got it. Then they apply a clustering algorithm, specifically k-means, but adapted because they're dealing with numerical predictions here, not categories.
Okay, like predicting C-peptide levels, not just yes or no.
Right. So this k-means algorithm looks at those prediction lists, those signatures, and it groups together the trees that have similar signatures. Trees that tend to make similar predictions across the training data get put in the same cluster.
Like finding groups of trees that think alike.
That's a good way to put it, yes.
And how many clusters, how many groups do they make?
They actually experimented with this. They set the number of clusters, k, to be different values, ranging from 5 up to 50 in steps of 5.
Ah, so they could create pruned forests of different sizes, like 5 trees, 10 trees, up to 50 trees.
Exactly. This corresponds to pruning levels from 99%, keeping only 5 out of 500, down to 90%, keeping 50 out of 500.
Okay, so they group the similar thinking trees. How do they get the final small forest from those groups? Do they average the trees in a cluster?
Simpler than that, actually. From each cluster, they just select one representative tree.
Just one. How do they pick the representative?
In this particular study, they chose the tree within each cluster that performed best, had the highest accuracy on the original training data itself.
Okay, so find the best performer within each group of similar trees.
Right. The paper mentions other ways you could potentially select the representative, maybe randomly, or based on how well it did on those out-of-bag samples we talked about earlier. But for this work, they used the best training accuracy within the cluster.
So if they created, say, 10 clusters.
Then the final CLUB-DRF model has exactly 10 trees, one representative from each of those 10 clusters. Its size is K.
That's quite elegant. You go from 500 potentially redundant trees down to maybe 10 or 20 carefully selected representatives.
That's the idea. Capture the essential diversity of the big forest in a much more compact form.
Okay, sounds promising in theory. How did it actually stack up when they tested it on that real medical data you mentioned, the diabetes, breast cancer, and Parkinson's sets?
Right, the practical test. They used 3 data sets: diabetes, predicting serum C-peptide levels.
Which relates to insulin production.
Correct. Then breast cancer, predicting the type, I believe, benign or malignant based on cell characteristics. And Parkinson's, predicting a symptom severity score.
So meaningful clinical predictions. How did they set up the test?
They used a pretty standard approach called holdout testing. They split each data set, used about 2/3 of the data, randomly chosen, to train the models, both the parent RF, the CLUB-DRF versions, and traditional RFs for comparison.
Okay.
And then they tested how well all these trained models performed on the remaining 1/3 of the data that the models had never seen before.
So a fair test of generalization. What were the key results? Did CLUB-DRF live up to the hype? Let's talk accuracy first.
The results were quite positive for CLUB-DRF. They looked at mean absolute error, or MAE, basically, how far off the predictions were on average.
Lower is better for MAE.
Lower is better, yes.
Yeah.
And across all three data sets, the CLUB-DRF models, regardless of their size from 5 to 50 trees, generally had lower MAE than both the original 500-tree parent RS and traditional random forests built with the same number of trees.
Wait, so even the tiny 5-tree CLB-DRF was often more accurate than a traditional 5-tree RF, and sometimes even beat the massive 500-tree original?
Yes. The bolded values in their results tables show that quite clearly. CLUB-DRF consistently achieved better MAE scores in most comparisons.
That's impressive. Better accuracy from a smaller model. What about other metrics? Did they look at anything else?
They also looked at R-squared, or R2.
Yeah.
This tells you, roughly, how much of the variability in the outcome the model can explain. Higher is better here, with 1.0 being a perfect explanation.
Okay, what did R-squared show?
For breast cancer and Parkinson's, CLUB-DRF performed really well, achieving R-squared values around 0.9.
So explaining 90% of the variance, that sounds high.
It is quite high,
Yeah.
especially compared to the traditional RFs. The best R-squared for traditional RFs on those datasets was much lower, around 0.7. So CLUB-DRF seemed much better at capturing the underlying patterns for those conditions.
Interesting. And the diabetes dataset, you mentioned it was maybe trickier.
It was. It's noted as being a small dataset, which can make modeling harder. The parent RF actually had a negative R-squared, meaning it performed worse than just predicting the average value. Yeah. But the CLUB-DRF models, especially the ones with 30 or more trees, managed to achieve positive R-squared values. Still not super high, but it suggests they were picking up some signal that the standard RF missed entirely.
So accuracy-wise, CLUB-DRF looks like a winner, or at least very competitive, even at small sizes. But the other big promise was speed, resource efficiency. Did they measure that?
They absolutely did. They measured the inference time per instance, or ITPI.
Yeah.
Basically, how long does it take the trained model to make one prediction for one new patient?
Faster is better, obviously.
Definitely. And the results here were also very favorable for CLUB-DRF. In almost all the comparisons, CLUB-DRF had a lower, meaning faster ITPI than a traditional RF of the exact same size.
So even comparing a 10-tree CLUB-DRF to a 10-tree traditional RF, the CLUB-DRF was usually faster.
Yes. Maybe not hugely faster in those direct size comparisons, but consistently faster.
But the real speed gain must come from comparing the small CLUB-DRF models to the original big one, right?
Oh, absolutely. That's where the difference is dramatic. Comparing, say, the 5-tree CLUB-RF to the 500-tree parent RF, the speed up in making a prediction was substantial, orders of magnitude faster, potentially.
Which is exactly what you'd want for running on a phone or a wearable.
Precisely. You get potentially better or similar accuracy, but with a prediction time that's drastically reduced because the model is so much smaller and simpler. Less memory needed, less processing power.
Okay, so pulling it all together. The key takeaway seems to be that this CLB-DRF method, using clustering to prune a random forest, really does seem to deliver on its promise.
It looks that way based on these experiments, yes. It managed to achieve strong, sometimes superior accuracy compared to traditional RFs.
While being significantly smaller and faster, especially compared to the large forest it originated from.
Right. The researchers suggest this improved performance likely comes from that clustering step, effectively identifying and preserving the most valuable and diverse predictive patterns from the parent RF while discarding redundancy.
Making it highly resource efficient. Suitable for those devices with limited horsepower, opening doors for more mobile health applications.
Exactly. You can imagine deploying these lean, fast, yet accurate models directly onto handheld devices for more personalized, real-time healthcare insights.
So, to recap for everyone listening, CLUB-DRF offers a clever way to shrink down powerful random forest models for healthcare predictions. It uses clustering to group similar trees and picks representatives,
resulting in a final model that's much smaller, predicts much faster, and according to this research, often maintains or even improves prediction accuracy.
which is a pretty compelling combination for healthcare analytics.
It certainly seems promising.
It really makes you wonder, doesn't it? If we can get these accurate predictions so much faster and on devices we carry around, how might that truly transform healthcare delivery? Especially thinking about remote areas or situations where quick decisions are critical.
That's the big question, isn't it? The potential is definitely there. But he also raises questions about validation, implementation, and, of course, ethical considerations as these tools become more integrated.
Definitely food for thought. What are the checks and balances needed as these powerful, efficient prediction models become more commonplace in managing our health?
A crucial ongoing discussion.
Thanks for walking us through this research today. Really fascinating stuff.
My pleasure. It's an exciting area.
And thank you for joining us on the deep dive. Until next time, keep exploring how technology continues to shape our world, including our health.